microphone. Microphone is working. Okay. Here we are. Okay, so Lucas wants to do this one, right?
I'm just nervous about the formatting of the answer.
Yeah, let's get the format of the answer. So Lucas, tell me what you have for the next number. Can you tell me what the next number is?
It would be 250 times 5.
Like that?
Yes.
Okay, so you know that the pattern is that the next number is the previous number times 5. Okay, next is 5 times previous. So Pearson wants to tell us what the starting number is, right?
Absolutely, it's 2.
Okay, so start at 2. Start at 2. That good? Now that's kind of using words. We don't like words, do we? You don't like words? No, none of us like words. We like numbers, we like letters and symbols. So what we're going to do is we're going to just change all that to symbols. So the next one is 5 times the previous one. The way I would write that is, well, I would say either something like this. A sub n is equal to 5 times a sub n minus 1. Does that work? And then start at 2. So Lucas, what do you want to call the starting number? A sub
0.
You could do that? Yeah, that's perfect.
So
You could have started at 1, a sub 1, a sub 0. I don't know. Does it specify that we're supposed to start at a sub? No, it doesn't.
I think the back of the book had a sub 0.
Well, okay.
So n is the number in the sequence.
This is a sub 0, a sub 1, a sub 2. So yeah, it's the position. It's like the house number on a street where all of these houses are holding numbers in them. And so here's who lives at house number 0, here's who lives at house number 1, and so on. And so to figure out the next one, multiply the previous one by 5, and you'll get the next one.
So are you allowed to have n by itself
In the formula?
formula?
Yeah, absolutely. In fact, let's see, is there one like that? I hope so.
For B, I did something like that, but I don't know if it was right.
Yeah, that looks good. So you guys have comments about this one? I didn't know if you were angry about this, and that's why there was this raging little. Okay, so the sub in is okay. Okay, so we got it now. Okay, well let's take a look at the B just to compare and contrast, because Lucas wants to know, can I have in as its own thing? Sure, you can do anything you want with this stuff. Well, maybe not anything, but 6, negative 18. Of course, we want to match the 54, negative 162. Okay, so Lucas, do you know what's next in this sequence?
Well, so 3, 4, 5. It would be negative 162 times 6.
Oh, crud. No, this isn't. No, this is not a good one, is it? Sorry. So, yeah, this doesn't have n in it, separate, sadly. Yeah, it's just times negative 3. This one's boring. Yeah, because 6 times negative 3.
The 18 times negative 3 is...
It's one of those odd numbers that don't seem like a short.
Okay, I didn't even check that. I was like, oh, it goes 3, 4, 5.
I wish it did. I wish it did. So is the next one 14 fifths, 28? No, that one's boring too. Those are all boring. These are boring. Okay. Well, then we need to solve these recurrences. So that's the next step. So let's take a look at this. So hang on to that homework for just a bit, and we will, oh, that's not what I want. We will use it in a bit. Let me just get this into the right place. Solving recurrences is what I want. Come on, buddy. And we're going to do this. So let's do, oh, that's right. We also have to do the tires. I'll have to go get the tires. Why is that so little? Yeah. So this is a recursive poster. This is in my, I was Googling pictures that were recursive. So recursive poster. I've got a recursive comic strip as well. I'll show you. And then this is amazing. I want this t-shirt. Well, not this t-shirt. You'll see what I mean. I really want a t-shirt like this, but with me instead of this guy. It's hilarious. But anyway, so recursive t-shirt. But anyway, let's go ahead and see if we can solve these recurrences. Okay, first of all, before we do this, let's do this. This is terminology. So a homogeneous recurrence is a recurrence that can be written like this. I know. What is that? That is so impossible to understand. And I've lost my Apple Pencil apparently. Did I stick it in?
It's underneath your computer.
Why is it under there? Oh yeah, it snuck under there. It's because I'm trying to keep, my computer died last time because it overheated. And so I'm trying to keep it as cool as possible. And I've got this to monitor. Of course, I can't really monitor. Oh, look, it's only 43. That's amazing. So it was like 110. Okay. That's Celsius, by the way. So like, yeah, oh, what? Is that funny?
Yeah.
There's 100, yeah, it crashed. It was like 110 degrees Celsius and it just blew. Just turned off.
What did you do to it?
I don't know. I guess I was running too many programs. You know, what do I have? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 16, 17, 18. I've got 18 things going on. I think it's the video recording software, and then I coupled that with this. So I think it was just the graphics. It was like overdoing it. I was using this along with the video recording, and it just blew. So I mean, we could see if it heats up. Just a minute. Oops, where'd it go? Okay. Okay. Here's what we're gonna do. Watch this. This will be fun. Okay. So if you want to, you can watch that 45 there. I'm gonna start the visualizer. So this is this thing. Let's do this. Give it a sec here. Okay, so here we go. So this is now look at it. It's jacked way up now. I don't know why. It's like this program just kills it.
70 degrees seems normal.
Okay, well, but then I didn't have it. I had it suspended. I had it right flat against this tabletop, and the vents here, they're just sucking nothing. Like there's no airflow. Because, yeah, so I think that's what did it. But it's just so funny to me that this program, this whatever this is, in order to use the camera, now let's see if it'll cool back down. I hope so. Yeah, now the max. So here's maximum, and there, yeah, it's dropping back down. I'm happy now. Okay. So what was I distracted for? What?
There's a temperature sensor built in.
Yeah. And I just, well, I downloaded this. It's open. If you want, you can download this as well. Open hardware monitor. I needed something so I could watch, and this one saves the data in a CSV file, so I can go back after our crash to see how hot it got. And yeah, it's like 110, 120. It kills your computer apparently. So there, problem solved. 47. Okay, enough of this. Okay, let's do this. So what does all this mean? I know it looks like a mess. So here's what it means. We have the Fibonacci numbers. The Fibonacci numbers is the previous one plus the previous 2 times ago. So those are the Fibonacci numbers. We're familiar with this. And so this is like 8 is equal to 5 plus 3. Sorry, my 5 looks like a 6. It's 5. And then the next one is 13 is equal to 8 plus 5. And then the next one is 21, which is equal to 13 plus 8. And that's where this business comes from. 1, 1, 2, 3, 5, 8, 13, 21, etc. Okay, so that we're familiar with. We're familiar with that sort of way of writing, or maybe you aren't yet, but here it makes more sense because you're saying, okay, next time I want to compute a number, I just look at the previous one and the one 2 times ago, add them together, and I get my Fibonacci number. So this is just saying that what we're going to do is instead of writing this Fibonacci sequence like that, we're going to write it like this. Fn minus Fn minus 1 minus Fn minus 2 is equal to 0. That's it. So we just move everything to the left, have 0 on the right, and we're all done. That look all right? Yeah, good. Okay, I think I realized where I went astray with the homework because there's this one minor little topic that would be helpful to be able to do the homework that I didn't cover, and it's not this. So let's just take a brief moment, interlude, and pull this up, and let's talk about what are called geometric sequences. If you've had Calculus 2, you might have some PTSD from geometric series, maybe, I don't know. That's like the sequences in series at the end of Calc 2. But anyway, geometric sequence is pretty straightforward. It's just to get the next number is equal to something times the previous number. In fact, all of the ones on your homework were geometric. Let me just show you. We have 2, 10, 50, 250, 12, 5. Oh. So this one, the next number, let's call it a sub n, is equal to 5 times a sub n minus 1. Next number, previous number, times 5. Whenever you have a geometric sequence, there's an easy formula. So this is where I failed. The easy formula is this. A sub n is always going to equal the first number times the something to the n power. Let me demonstrate, okay, just so that you can see this in action. So in this case, a sub n is equal to the first number times the something here is the 5 times 5 times 5 times 5. So you saw the pattern, 5 to the n. Let's double check. A sub 0 is 2 times 5 to the 0, which is 2. So far, so good? Now, if you use this formula, you always have to start with a sub 0 is the first number. So you can't start at 1. Sometimes you can finagle your way around this, but let's just do it this way because it's easiest. Anyway, A1, what is A1 here? A1 is going to be 2 times 5 to the first, which is 10. That's pretty cool. And then a sub 2 is 2 times 5 to the second, which is 50. Ooh, I see a pattern. And a sub 100, ooh, what is a sub 100? This threaten with this, right? If I can find it. So does someone want to share your a sub 100 with me? You don't have to tell me. Here, I'll give you there. Don't do that part. Just do the stuff between. Yeah, what do you got? Yeah, whatever that is. It's going to be some big number. It's like on the order of 10 to the 60th or something. I don't know. You could do it on your calculator and you get some scientific notation for it. But yeah, beautiful. So this gives us a way of computing these things. So this is called the explicit formula. We did go over the explicit formula last time, but we never connected the two. So here's the connection, is if you have a geometric series, or sequence, then you can just take the geometric, so if it's multiplied by the same thing, it's pretty easy to translate the recursive formula, this one is recursive, to explicit. So pretty easy to make that translation with geometric sequences. And so now we can actually do number 2, so we might as well do it now, because actually all of, this is all easy at this point. Let me double check. Yes. Let's just demonstrate this, so you can do this for next time. Add it to the homework I'm going to give you if we get to it. I might have to add it to the homework. But here, let's take a peek here at number 2, part A, and then we'll also do number 2, part C. I'll let you do the other two yourselves. So number 2, part A, I have this. A sub n is, A sub n minus 1.5 A sub n minus 1 is equal to 0. This doesn't have a unique solution.
Is it supposed to be a to the n plus 1?
Oh,
That's
sorry.
what I had written down.
Yeah, it is. I'm sorry, I've just, let's do this. N plus 1, there. Okay, so let's see. The solution to this is you get A sub n plus 1 is equal to 1.5 A sub n. So let's see. Let's go back to this in the blue here. The something for this one is 1.5. Just like up here, the something was 5. So that's the first thing to note, is that the something is 1.5, which means that when I get my formula, I'm going to have something, it's 1.5 to the n. That's not the whole formula, though, because the whole formula says you take the first number times the something to the nth power. Well, here's the problem with this one, is it doesn't tell me what the first number is for this particular problem, does it? It just says this is all it says. So what's the first number? Well, I don't know, so I'm just going to call it a sub 0. And that's going to be my answer.
What's the difference between the a to the n plus 1 and the a to the n minus 1?
Okay, so it's just a perspective. Here. Okay, let me do this. So a sub n plus 1 is equal to 5a sub n. And then compare that to a sub n is 5a sub n minus 1. So here's the perspective that I always think of when I think of those two. It's the same formula. So let's talk about this one first, this one. So here, I am standing at, here we go, let's do this. What am I doing? Get rid of that circle. Just a sec. Let me put boxes. Oh, here. Houses. This is house 0. This is house 1. This is house 2. And so on. Okay, so in this, I'm standing here. And I want to know, what is the number here? And to figure out the number here, I have to look back to the number here, n minus 1. And so I'm just standing there, there, and I say, okay, I'll take whatever's here. So whatever is over here, I'll multiply it by 5 to figure out what's here. So that's my perspective in that case. When I look at this, the way I imagine it is that I'm actually standing a little further down the road, right here. And I want to know what is going on in this house. And so to figure out what's here, I look back at that. But it's the same exact, you're going to multiply the previous one by 5. So whether I'm standing here in front of this house or this one, I say, okay, what's going on in the house to the left, multiply it by 5, and I'll get what I'm at. So yeah, it's just a placeholder. I mean, you could do anything you want. In fact, as long as it makes sense, let's see, we could do this, which would be a little silly, but no one does this. You could do a(n plus 5 is equal to 5 times a sub n plus 4. That expresses the same idea. To get this number, take the previous number times 5. In fact, I could do it this way. A smiley face is equal to 5a smiley face minus 1. You know, it's just, these are placeholders. They're just saying, to figure out what's going on here, take 5 times the previous. So, but I would never do smiley face. I would never do this. That's ridiculous. Okay. Moving back. Here's what I'm doing. So is everyone happy with 2a though? Other than that issue with the a minus n plus 1, n minus 1. Oh yeah, let's do 2.
I have another question.
Yeah, yeah.
So the 1.5, that's with the a n. Let's say it was with the a to the n plus 1.
Mm-hmm.
Would that still be our number that we're like multiplying by?
No. So actually 2c is like that. So we'll get there. Oh, by the way, this has a name. So back in calculus, if you took calculus 2, that was called the common ratio. So you could think of this ratio of, you know, the next time I'm going to multiply by 5 or 1.4, whatever it is. And so it's this common ratio that you're always multiplying by this each time. And that's the ratio between the successive terms in the sequence. That's why it's called the common ratio. But we don't need to get into that too much. That's more useful when we're talking formulas for summations, which I know you want to do summations, but we're not going to. Let's take a look at C so we can get to Peyton's second question, which is what happens if the number is in front of the a(n plus 1 instead of being in front of the a(n)? Well, this one actually is a bonus, the bonus question, and that is what happens if there's numbers in front of both of them? Well, let's deal with this. So, oh, and they give us a starting point, don't they? So they say we're starting at a1 equals 5. Okay, so if you have a situation like this, proceed the same way. Notice what I did was I took this and I solved for a sub n plus 1. So you solve for that. So what do we got here? We have 3a(n plus 1 is equal to 4a(n). Does that look right? And then divide by 3, and that gets rid of that number. Yeah.
So are you always going to put the one that's the next term on the left side?
Mm-hmm. In this case. So there will be a situation, but that's maybe on Monday. We'll see.
So
Yeah.
Can you translate a(n plus 1 to a(n and then a(n on the right side to a(n minus 1?
You sure can. That's just changing your perspective. If you prefer to do it that way, that's fine. All this is saying is that to figure out one of the numbers in the sequence, you just look at the previous number, however you want to number them, however you want to refer to them. You say, if I want to know what's going on here, I'm going to look back there and multiply by 4/3.
So would both representations be correct?
Yeah.
So there isn't like a preferred way. That's why I guess
I noticed that this book seems to prefer this, although no,
they
go both ways. Yeah, because looking at number 2, A and C have it with the plus 1, and B and D have it with the n minus 1, which means you would put a sub n on the left and a n minus 1 on the right. So yeah, the biggest one, what Sarah said is correct. You put whatever's the biggest, that goes on the left. All right, now we got to deal with another issue, and that is the starting point. So this starting point here is not the same as the starting point here. The starting point is always going to be a0. So I guess we're gonna have to do a little bit of thinking. You could probably figure this out without doing much thinking, but I'm gonna do this anyway. Let's actually write down some of the numbers in this sequence. Let's see, I'll put them down here. So we start with a sub 1 is the number 5. That's what it says, right? Yeah, a sub 1 is the number 5, which means a sub 2 is the number 20/3. And then a sub 3 is this number, 100. Sorry, not 100. I can't do math apparently. 80/9. So you see the pattern? We're always multiplying by 4/3 to get the next number. Let's just do one more just to be sure. The next number is going to be 320/27. That's a sub 4. So it's not that hard. Yeah.
If we're doing something like this, is there a certain number of iterations you want us to write down?
Only if I specify. Then, but otherwise, I'm not going to make you do this. I mean, like if I ask you what's the first 4 terms of this sequence, there they are. So on a test, I'll do that. Okay, but here's the problem: is that this formula up here has a sub 0. That's what it means by the first number, because it's like Python or a computer language that's index is starting at 0 instead of 1. So this formula, we have to have a 0. So can you go backwards? Can anyone see how you would go backwards in this to get the previous number? This a0? Yeah, what do you think? Yeah, divide by 4/3. If you have to multiply by 4/3 to get the next one, let's just divide by 4/3. So you get 15/4. You can double check my math, or rather, I can blame Gina if it's wrong. Double check her math. But yeah, 15/4 times 4/3 is 5. So anyway, there's my starting point. Now let's just put it all together. So the formula that we want is a sub n is the starting point times the something to the nth power. And that's the formula. You can double check the formula. In fact, I encourage you to do that. Plug 4 into this, and you'll get this number. So you get 4/3 to the 4th power. Oh yeah, I guess you could fold this into here. So it's 4 to the n minus 1 over 3 to the n. Oh, you're right. Cancel both of them. 4/3 to the n minus 1. Nice. Yeah, I don't mind if you want to do it that way. 5 times 4/3 to the n minus 1. That works as well. It's the same formula. I mean, it's exactly the same. But some yeah, you do it this way. It's beautiful. I love it.
Because if you multiply, does it matter which one goes first, or do you want it in that set form?
What do you mean?
Like if I did 4/3 to the n times 15/4.
You're in modern algebra, aren't you?
I know, but I just listen.
And this is an abelian group, right?
Yeah, I just want
Multiplication?
to make sure
Yeah. No, I'm cool with that. As long as it's equivalent. I mean, if you want to really drive me nuts, you could do this. We could do 150 times 4/3 to the n, all divided by 40 or something like that. I don't know. Or times 1 over 40, which is completely, why would you do this? I don't know. Just to make it hard for me to grade your paper? Yeah, you don't want to do that. Make it easy. Wow. All right, so we've done the preliminaries. Is everyone covered? So you think you can do B and D? Hopefully. D's not bad. You can do it. I'm confident in you. Okay, well, let's get back to what we're supposed to be doing, which is right here. Okay, so the idea here is that I want to, so these recurrences, this is called a second order recurrence because there are 2 previous terms. The geometric series, or sequence, sorry. Geometric sequence is a first order recurrence because you're just looking back to one term ago. Here you're looking 2 terms ago. So what's going on back there? And this could have been written here just so that you know. And you could have written this like this. And once again, it is just a matter of perspective. So these are equivalent. All I'm saying is that this term, I don't care what you have for the index. Whatever term this is, you look at the previous term plus the 2 terms ago. So either one of these works. But in both cases, that's what we call standard order or standard form. Okay, so how do we solve these? Now, some of you are differential equations people, and it's going to feel somewhat familiar to you, this process, because what we're going to do, I've got a slide describing this, but what we're going to do is we're going to guess and check. And the thing we're going to guess and check with is we're going to guess and check using the form of the, here we are. Where's my form? Sorry. There it is. There it is. Okay, so we're going to use this as our guess. Let me show you what I mean. Let's see. I need to make this big. Okay, good. So let's see. Let me take a relatively easy recursion. Let's explore the recursion briefly, and then we'll actually see what it looks like. So I'll call this the A sequence. So we're going to say A sub n. I'm going to write it like this first because it'll be easier for me to do. So this is going to be A sub n is equal to, let's think about this for just a minute. How about 4? I hope this works. It's always dangerous to do math on the fly. 3A sub n minus 2. Okay, let's just, and I need to have a starting point. A0 is going to be 0, and A1 is going to be 1, just to make things easy. So I need to know what is A2, what is A3, what is A4. We'll start with those, and then we will solve this recurrence. We'll use this as the, and then I'll go back to the PowerPoint in just a minute so we can see how this relates. So let me do A sub 2 for you. A sub 2 is 4 times A1 minus 3 times A0, which in this case is 4 times 1 minus 3 times 0, because I'm using these things in here, and that equals 4. So far, so good? Okay, let's see how you do with this. So we'll do this a little bit at a time. Don't fret. I will help you. So you're not here. You can't do it. Lucas can do it, though. Lucas, how would you write A sub 3 like this, just in terms of A2 and A1?
So it would be 4A2
Very.
sub 2 minus 3A sub 1.
Very nice. That's beautiful. Okay, now we need to make the substitution. Sarah, what do you get? Or just tell me what to write. Like, do this part for me.
So 4 times 4 minus 3 times 1.
Very nice. Very nice. So good. It's so good. Joseph, what's the final answer for this thing? Almost.
That's the question.
You said 13, right? Is that what you said?
Yeah.
That's what I thought. Okay, yeah, I just didn't hear you well. Yeah, my calculator is always a little bit rusty until I get a little bit of caffeine in me. So I sympathize. Okay, very nice. So there it is. Any questions about A3? Just want to make sure that you understand what my recursion is doing. Okay, now let's do A4 just for fun. Joshua, tell me the formula in terms of A3 and A2.
It'd be 4 times A3 minus 3 times A2.
Beautiful. Let's plug it in. Where are we, Gina? What do you got for plugging? What do you plug in here?
4 times 13 minus 3 times 4.
All right, that's beautiful. And then Pearson, what's that final answer there? All right, no, this one's actually kind of cool. Notice that you have 4 times 13 minus 4 times 3, which is the same as 4 times 13 minus 3. What's 13 minus 3?
10.
What's 4 times 10?
40.
Beautiful. Very nice. So 40. Okay, so you can see where, I know, I'm making you do your arithmetic in your head, but you have a calculator, don't you? If you don't, you can always borrow one. It's in your home. Yeah, what's up, Gina?
So, the difference between this and the geometric series. So geometric series looks one back.
Yeah.
And the whole point with this is that it just looks two back.
That's right. Yeah, and because there are a bunch of different recursions, like the domino thing that we did last time with those little cubes, and like the tires, if we got to the tires, which we'll get to the tires on Monday, I guess. But anyway, there are a bunch of things like that look two back instead of looking one back. And then there are some that look three back, and there are even others that look even further back. So it just depends on what sort of problem you're trying to solve. But this one's just fictitious, just made it up. Okay, so here's what we want to do. This is the point of this. Will it go up there? Oh, it did go up there, didn't it? The point of this is I want to come up with the formula. And you remember last time I had the Benet's formula that f sub n is 1 plus radical 5 over 2 to the n minus 1 minus radical 5 over 2 to the n all over radical 5. So this is Benet's formula. It'd be kind of cool if we learned where that came from. Oh, that's hard to read. Don't worry. We're going to actually derive that. But here's how you do this, is we take a guess. So I'm not going to let you write all this down for now. I'm just going to do one at a time. We'll do one step at a time. So the first step is to guess. We're going to take a guess, and we're going to generate an equation that we're going to call the characteristic equation from that guess. And whoops, let's go back here. Is that going to be little? Of course it is. So like I said, if you're a differential equations person, this will seem super familiar. So here's my guess. So my guess is that a sub n is equal to r to the n. And you might say, where are you getting r to the n from? And the reason I'm using r to the n is because this is what the solution to the geometric series is, and this feels sort of like it's geometric. I mean, you've got an additional term here, but it's sort of similar. And so we're going to use this as our guess. So let's take this guess, and we're going to stick it into here. I suppose I need to know if I'm going to use this, a sub n minus 1 is r to the n minus 1, and a sub n minus 2 is r to the n minus 2. Also, before I plug this in, let me erase this stuff up here so it doesn't bother me. Also, what we're going to do is we're going to take this stuff, this one here, sorry. This, yeah, we'll eventually do this here. But this stuff, I'm going to rewrite this into the standard form, which is to have all of the stuff on the left and 0 on the right. So write it like this, then we're going to plug in this stuff. So let's see, we have r to the n minus 4r to the n minus 1 plus 3r to the n minus 2 equals 0. This thing here is called the characteristic equation for this particular recurrence. And like I said, if you're familiar with the differential equations, this is the analog of the characteristic equation for a second order differential equation. If you don't know what those words mean, don't worry. It's not gonna hurt you. Sorry, I just wanted to put it over here where I could look at it. Oh, we should be able to see both for a bit. So yeah, I've got two of them now. One of them is going to not have the box though. So do you have any questions about where the characteristic equation came from? So we're just taking a guess. This is a guess. It feels like, why can we get, well, mathematicians do this all the time. Okay, so next we go back to this. And the next step, we've got this characteristic equation, and now we're going to solve for r. I have an equation. It's a polynomial equation. I can solve for r. Let me go back here. Where is my equation? There it is. I'm just going to solve this for r. Go ahead and do that. You can factor this. Come on. I know it's scary, but I'm pretty sure you can factor that. Oh, let me help you with the first step, just in case you're not sure where to go with this. I'm going to factor out the common factor of r to the n minus 2, which will leave me with r squared minus 4 times r plus 3. So that may be unfamiliar to you because these exponents are weird, aren't they? But once I pull out this r to the n minus 2, now you might still be dazzled by this, but you can check to see that this is correct. R to the n minus 2 times r squared is r to the n. R to the n minus 2 times negative 4r is negative 4r to the n minus 1. And then this times 3, of course, is that. So you can factor, I'm sure you can factor. In fact, I'm so confident I'm just going to pick someone. All right, Sam, can you factor that trinomial? I have faith. I'll get you started. Oh, don't even worry about the middle one right now. Just come up with two numbers that multiply together to be 3. 3 and 1, good. 3 and 1. And now, do I want to add or subtract those? Yeah, subtract them. Now we double check. So yeah, I know Sam had factoring back in 8th grade because he was one of these advanced students. It's been a long time, so I appreciate that, but I'm glad you gave it a go and it did a good job. But yeah, so the way I tell students when especially here, is just take a guess, check. The way you check is 3 times r, and then r times 1, add those together and you get 4. So if you're trying to remember the pattern, Sam, it's that the product of these two numbers should equal 3. The sum of the two numbers should equal 4 or negative 4. That isn't as easy to do when there's a coefficient to the r there, but I guess we're never going to have that. So yeah, you can use that formula. So let's go ahead, and Peyton is going to do the actual solutions. There are 3 solutions to this, aren't there? Because you have 3 factors. Whoops, I just erased one of them. Okay, here it is. Let me highlight, or here, I'll underline them with this weird, looks like a crayon or something. So there's 3 factors. That should give me 3 solutions. So what are those 3 solutions, Peyton?
3, 1, and 0.
It is 0. Very good. Yeah. You'll always get 0. 0 is kind of this fake solution because that doesn't make a lot of sense to say you've got 0. So here's how you're going to, okay, we're not quite done. Let's see. I was getting excited. Okay. Next, you're going to write your solution like this. Oh, I know. What in the world does that mean? Okay, let me explain. Let me do it here. Okay. So here's what I mean by this. So my solution, what are we doing? A, capital A? I got to zoom out a bit. It's capital A. Okay, so now I take these. Oh no, I erased a bunch again. I always keep switching back to the eraser. Okay, so we have these 3 solutions. And as I mentioned, the 0 is always a solution that you're going to ignore. But I'm going to not ignore it just for a minute. So my solution, I'm going to do this. A sub n is going to be, I'm going to start with the 3. So I have C1, I don't care what I call this, C1, C0, doesn't matter, times r to the n, because that's what we were starting with r to the n at the beginning, plus C2 times, whoops, oh yeah, it's 1, times 1 to the n, that's this one, so that and that, And then I'll have C3 times 0 to the n, which is silly because we know that 0 to the n is just 0, right? And so that's just 0. So let me rewrite this. The way that you're going to really do this is you will ignore the 0. You will only use the 3 to the n and 1 to the n. So far, all right? Yeah, what do you think?
Yeah, how do you know which one goes first?
Doesn't matter. And this gets back to the modern algebra thing, that addition is also commutative.
No, sorry, I mean, of the 1 and the 3, how do you know which one's supposed to be on C1 and which one's supposed to be on C2?
Well, these indices are they're just placeholders for now. You can rename, this could be C4, and this could be C23. You name them whatever you want, but that's kind of dumb, isn't it? I mean, I wouldn't want to do that to you. So let's go back to C1 and C2. Okay, we're almost done. Last step. Final step is use the initial conditions to solve for the C's. Okay, that's going to take some little bit more explanation. So what does that mean? Well, where are the initial conditions? Here they are, right up here. Those are the initial conditions. It's like, where did we start originally? We started over here. A0 was 0, A1 was 1. Okay, so here's how I'm going to do this. A0 is 0, A1 is 1. I do it like this. A0 equals 0, and A1 equals 1. Now, here's the tricky part, is I need to actually think in terms of what is going to happen when I change in to 0 up here. So what that's going to do is I'll get C1 times 3 to the 0 plus C2 times 1 to the 0. Sarah, you know what 3 to the 0 is, don't you?
1.
Yeah, it's just 1. So this is going to be C1, and of course 1 to the 0. 1 to any power is just 1. Well, look at that. Next, I'm going to do the same thing for the other initial condition, and that is A1 is 1. And here I'm going to change those n's to 1s. So I have C1 times 3 to the first plus C2 times, 1 to the first. 1 to the first should equal 1. So this is 3C1 plus C2 equals 1. I need to solve these two equations for those two unknowns. And I know Joseph can do this. Well, just get us started, because I don't want to take the fun away from everyone else. What's your first step? You know, like, you probably remember there's a couple different ways to solve two equations with two unknowns. But what's your impulse, your inclination, intuition?
Probably subtract that one from that one.
Oh, nice. So you're using elimination. I love elimination. So the two methods are substitution and elimination. So I love Joseph's method of elimination. It's my favorite. But if you were thinking, I'm going to solve this for C2 and plug that in over here, that's totally fine. That's called substitution. I like the elimination, though, so we're going to go with it. So what I'll do is I'll just take this equation and write it down here. And then I'm going to subtract the green from the brown. And that's going to give me orange. Oh, maybe. Does it work? Yeah. Is that visible? Okay, so this gives me 2C1 is equal to 1. Is that good? And that C1 equals 1/2, which means that C2 is negative 1/2. How do I know that? Well, it's from this. So if I take this, stick it up there, and then that gives me this. We're almost done. The final step is to put it all together. Let's write the final solution. I'm going to write it down here. Apparently, it's going to bump into this other junk. Okay, so your final solution, A sub n is equal to C1 times whatever this number was, minus C2 times whatever this number was. And I know that 1 to the n is just 1, so I suppose I could just leave that off, but I'm going to leave it on for now. Now, I just want to test this out. It's always good to test it out. Let's test it out with A4, because we know what A4 is supposed to be.
Is C1 the negative 1/2, or was that C2?
That was C2.
C2.
And so here, so getting, now let's just talk about Gina's original question. Oh, it's time to go. Is that if you switched those, if you called this C2 and this C1, then it would just change the values of these two things. And you notice that we don't care what C1 and C2, you could name them whatever we want. Here's our solution. Let me just do this real quick. A sub 4 is 1/2 times 3 to the 4th minus 1/2, which is, oh, look, it's 40. Actually, it is. 81 is 3 to the 4th. Half of 3 to the 4th is 40.5. And then you subtract off 1/2 and you get 40, which is exactly what we wanted. Okay, for homework for Monday, just do the rest of whatever you were supposed to do for today. And then we'll do more of this on Monday. And the homework that says it's due Monday will be due when, I'm just going to shove it all back. I'm flexible. Make sure you, when we get end of course surveys, when it says, is he flexible? Be like 5. Actually, all of the questions, 5. I mean, that's the easy way to go. 5, 5, 5, 5, 5. Oh, stop the recording so you can come and talk if you want to. Stop the recording.